Okay, hello, I'm Viviane Choykani again. I will be explaining you the last chapter in acid base, which is chapter 7. Let's start by the first session of this chapter entitled Reaction between a weak acid and a strong base, and the reaction between a weak base and a strong acid. Let's start first of all by listing the objectives of this chapter. After all, it's one objective, which is to master the pH metric study of the reaction between a weak acid and a strong base. Many sub-objectives derive from this big one. The first one is to write the titration equation, to determine its Kr, and to list its characteristics. Then, you have to describe the shape of the titration curve that it will be obtained. And you have to explain the value of pH at half equivalence. It's something new, this term. You will understand it after a while. And you have to explain the value of pH at equivalence. So let's start first of all by the reaction between a weak acid and a strong base. We know that the reaction between the ethanoic acid, we know it's ethanoic acid, it's a weak base, with a strong base. Ethanoic acid is a weak acid. When reacting with a strong base, which is HO- that comes, for example, from a solution of sodium hydroxide, this reaction is complete and rapid. Because it is complete, it's written here not in a reversible way. It's a complete reaction. So this is the ethanoic acid, this is the HO-, and those are the products obtained. Now, in this case, as we did in chapter 6, what are the species present at the beginning of the experiment? We have HO- deriving from the strong base, and we have CH3COH. So the strongest base will react with the strongest acid as it is shown here in this equation. In fact, the species present in the solution, as we said, are the one shown on the pKa axis. Na plus definitely is a spectator ion, as explained previously. Now, pKa2 minus pKa1, it is equal to 14 here, because this is the base and this is the acid. It's equal to 14 minus 4.8. So for this reaction, what about it's the expression of Kr? As seen previously, Kr, it is equal to the following. Okay, this is in general for any strong bases when reacting with an acid. Now, by multiplying the numerator here and the denominator here by H3O+, and by writing it the same equation here, it is written in a different way, by separating the product here H3O+, and here H3O+, this implies that Kr equal Ka over Kw. This is not something new. The expression of Kr can be written in the form of the following as seen previously. So you have to repeat this when the question is to determine Kr as seen in chapter 6. And finally, you will determine that, or you will find that Kr is equal to 10 exponent 9.2, that is much greater than 10 to the exponent 4. Thus, this reaction can serve for titration because it is complete. Okay, now let's do, after determining that this reaction is complete and it can be used for titration, let's start by a pH metric study for the reaction between a weak acid and a strong base. To study the pH metric, we have to consider a practical example. Actually, it is the one figuring in your textbook to page 165, the activity one. I don't rely a lot about this given, but I will tell you that it's copied from your book as is. And you have here in a beaker, the acid is found in a beaker with an initial volume 20 milliliter and with the concentration of the acid 0.01. And in the burette, we will put NaOH definitely in the burette because it is a kind of titration. The concentration of the base would be 20 millimole per liter minus 1. And the volume of NaOH would be determined at equivalence, okay, according using a pH meter. Now, using a pH meter, we follow the variation of the pH and we obtained these values of pH measured by a pH meter, as we said, at each addition, at each 1 milliliter added of the base. Okay, now this table will allow us to draw the curve. But before, this is a slide just to remind you about the setup used in titration. I don't have to repeat, but in our example, in the burette here, I have the sodium hydroxide solution, which is called the titrant one of known concentration. And also I have here the ethanoic acid to be titrated. And here is the pH meter, and look at its electrode that must be dipped here in the solution to read the value of pH at each addition of an AOH. Now, this is the titration curve obtained, as I said, based on the numerical values given previously. What do we have to do now? We have to study this curve, as we said in our objective. How to study this curve? Let's study the shape of the curve. You notice here that, first of all, we have this part, which is called AB, that first is colored by red. The second part, it is BC. Now it is colored by red. The third part, sorry. Okay, so we have to start by the first part. As you can see, the curve is increasing because at the beginning we have an acid on which we are adding a base. So the curve is increasing and it consists of 4 parts. Pay attention to this because this is different from the titration of a strong acid with a strong base, because there the curve was consisting of only 3 parts. Let's start the first part, which is AB. Here also I mentioned the numerical values because based on the activity, but in if you are asked in an exam to write it, you don't have to mention the numerical values, but to understand what am I working here on this in this case specifically. The first part, AB. Look at AB. This is a net difference. Here there is a net difference between the titration of strong acid with a strong base. We have here the graph that increases relatively in a rapid way here. The second part is actually BC. Look here at BC from here to here. It is almost, the variation of the pH here is slight. It means there is an increase in the pH because definitely we are adding a base into the beaker, but this increase is really slow. Okay, this is what did we call previously a plateau. And you have to pay attention that here I have something called an inflection point. What are the coordinates of these inflection point? They are VB equal VBE over 2. This is the volume of the base here, and which is equal to 10 milliliter in our case, and the pH is found to be equal to the pKa of the acid-base couple used. In our case, it's the ethanoic acid, so the pKa is equal to 4.8. As I said, this is found experimentally. Again, now look at the red part here, CD, that is colored now CD. What is that part? It is the third part, which is called CD. The pH here increases rapidly. There is a sudden jump of pH, and definitely we have the second inflection point, which is the equivalence point that has a coordinate VB equivalence and pH equivalence. And after that, we have the last part, which is DF, where we have a second plateau with a slight increase in the pH that tends to a horizontal asymptote, as you can see here. So this is the study of the curve. Now, the equation of the titration. Once we mentioned the word titration, with no doubt, without calculating Kr, directly the equation is written in the form of a of a total reaction. Now, what about the deduction or the determination of the equivalence point? This paragraph, I will not read it. I wrote it just as a revision to what we have seen in chapter 5 when we determined the equivalence point upon the titration of a strong acid with a strong base and vice versa. So the method of the parallel two tangents. So you have just to read it and to remember it. The most important is how to explain that the pH at half equivalence is equal to the pKa of the acid-base pair used. Look how. The following table shows the composition of the reactional medium at different instants. Pay attention to this. This is the titration equation. It is a complete one. We have in the beaker the weak acid, which is CH3COH, and in the burette OH- that is added point by point. The product when they react together in the beaker are the acetate ion and H2O, which is the solvent. Now at T0 in the beaker we have only the acid. We don't have a base, and definitely we don't have the product. Pay attention here. This is a complete reaction. It means a complete one, yes. It is not a reversible one. So although I drew here a table, this doesn't mean that I'm working with a reversible reaction. So you have to deal with it according to the study, to the stoichiometric study done in grade 10 and in grade 11 as a typical equation, not a reversible, so not an equilibrium one. So as we said, at T0 we have N0 of this reactant in the beaker, which is the acid. Now at T-half equivalence, what's the meaning of T-half equivalence? It means the half amount of the acid found initially in the beaker has reacted. Now, I will write this one. At T-half equivalence, as I said, the amount of the acid reacted is N0 over 2. What does that mean? Since N0 over 2 has reacted, it means the remaining at T-half of CH3COH, it is the initial number N0 minus the number of mole that has been reacted here. So the remaining is also N0 over 2. Now when CH3COH reacts, actually it reacts with OH minus, but here I don't care about the amount because it's 0 in the beaker, even if it is added in the burette, because so far this is a limiting one. And CH3COH formed has also N0 over 2 as the number of mole. Why? Because N of the acid here that has reacted, it is equal to N of CH3COO minus formed. It is equal to N0 over 2, knowing that the N CH3COH reacted, it is N0 over 2. So at half equivalence in the beaker, we have the acid and it is conjugate base. Forget now about these two values we don't have, or you can examine it yourself. But I care now about this point. What does that mean? This implies that I have the acid and its conjugate base. So, according to Henderson-Hasselbalch equation, we can find that the pH is equal to the pKa plus log to the base over the acid seen in the previous lesson. What is the value, the concentration of this one? You know, it is equal to this one because we have the same number of mole of the acid and the base. So at half equivalence point, the pH, it is equal to pKa. And this is a very important thing to be memorized upon titration of a weak acid with a strong base. Always at half equivalence, the pH is equal to pKa, and this is why we saw it like this on the graph, on the curve. Now, how to explain that pHe is basic? As we saw there, pH is not equal to 7 on the graph. Why it's not equal to 7? Let's refer to our pKa axis. At the beginning of the titration, we had OH minus in the burette and CH3COH in the beaker. Now at the end, it is a total reaction, a complete reaction. Complete, it means there is no more in the beaker, neither HO minus nor CH3COH. Look here, imagine this is the titration apparatus. After adding the necessary volume of NaOH to reach equivalence in the beaker, there is no more acid. There exists only what? The ion or the conjugate base of the acid. But also there exists water in the beaker. One can think that this conjugate base, can react with water. But actually, since we are working here against gamma rule, look how, against gamma rule, we have to find Kr. Without finding Kr, after all, those two chemical species that are present at equivalence, they can react how? In a reversible way. Pay attention that at pH equivalence, if you have to determine the pH, we have to mention all the species present. After all, they are Na plus coming from NaOH, which is an indifferent ion. We have H2O that is neutral, and we have this species we talked about, which is the base. Now, as we said, CH3CO minus that is here reacts with water in a reversible way, producing what? Producing again some amount of weak acid, and what is important here, it is HO minus. So the presence of HO minus, even in a small amount, it turns what? The medium basic. So I repeat, at equivalence, the pH is not equal to 7 because we have, due to this reaction, or simply you can say due to what? To the appearance of the conjugate base of the acid. Since this conjugate base exists, the pH is basic. Here, finally, we have to do a comparison between the two curves of titration. Here we have a strong acid and a strong base as studied in chapter 5, and here weak acid with a strong base. Look at the differences that are summarized in this table. Here, the curve consisted, as you remembered, of 3 parts with an inflection point. It means with 1 inflection point. Here, 4 parts with 2 inflection points. Now, the equivalence points E here, which is determined in both cases according to the parallel, to the 2 parallel tangents. What are the coordinates of this equivalence point? It is VB equivalence. It means the V of the base added at equivalence, and the pH is always 7 here. Here is what VB equivalence, definitely the amount of the base added, but pH is always basic. Why? As we saw previously, because we have the conjugate base of the weak acid. Half equivalence here, it doesn't exist. It's something that does not exist when we talked about strong acid and strong base. Here, half equivalence, it has a volume, the value of its abscissa. It's V base equivalence over 2, and the pH is always equal to pKa. This is something very important. Now, when we are far from the equivalence point, it means upon adding from the burette a volume of the base that is greater than the volume added at equivalence, because we are continuing to add, the curve will have an asymptote for pH equal 14 plus log Cb, and the curve there will have also an identical asymptote. So this is our objectives for today. You have please to solve as direct application numbers 1, 2, 3, and 4 in your textbook. I will thank you again for your attention.